Good day, everyone. My name is Vladislav Korzun. I am a PhD student at MIPT, and today I will describe some approaches for automatic gesture and facial expression generation. But before we look at the articles themselves, let me give you a general overview of audio and video data processing. That could help us to better understand the considered approaches. Most of current works uses an audio signal as input, and there are many ways to represent audio data. So, on the slide you can see different audio representations. The most basic is waveforms, an overall amplitude through the time. This representation does not give us a frequency distribution, so we don't know of what components sounds consists of the particular moment. However, if we take a sliding window of audio signal and apply to it the Fourier transform, we could get an audio representation in frequency domain, the spectrum. The most used audio representations are Mel frequency capture coefficients, or MFCCs, and spectrograms, obtained from spectrum by scaling its magnitudes to reduce amplitude differences. The original spectrum is rarely used because human subjective scale of perception of sound differs from linear Hertz scale. So, to reduce basic frequencies representation to the relevant for human perception, the Mel scale was developed. The name Mel comes from the word melody to indicate that the scale is based on pitch comparisons. On this slide, you can see how we can receive one form of audio representation from another. So, the Mel frequency capture coefficients are obtained from Mel spectrogram via discrete cosine transform. Fortunately, these methods are already implemented in packages like Librosa, and we don't need to implement our own transforms. Here you can see an example of reading audio file and showing its waveforms. Then we transform this waveform into MFCCs and scale it to see the difference in coefficients. So, now we can work with audio and represent it in a form appropriate for machine learning algorithm. Instead of generating video directly from speech, researchers first generate landmarks, the key point of human body or face. These landmarks could be received from recordings of talking people via motion or video capture. First approach uses special equipment for tracking markers attached to an actor. This method is very precise but expensive. The second approach is based on algorithm, including machine learning. It could detect facial landmarks on raw picture or videos. So, let's look at an example of using one of the automatic facial landmark detection. First, it detects the rectangles containing faces. Then, for each face, it predicts 68 facial landmarks, and this model is based on IBAC 300W dataset. So, there are other models with, for example, 194 points. So, we can represent audio signal as input and can receive facial landmarks from video as output for our algorithm. Now, we need data to train it. Of course, we can get a lot of videos from YouTube and have a lot of problems with data processing. But are there any specialized corpora for our particular task? The answer is yes. I found at least 2 open corpora of talking people. The first corpus is Lombard grid. It contains 5,390 shots where actor says very short phrases on the front camera. The audio and video tracks are separated by different files, and there is a phonetic markup. The second corpus is modality corpus. It contains 30 hours of multimodal high-res recordings with textual markup and audio recorded on different microphones. Its subcorpus, allophone corpus, also contained facial motion capture recording. Okay, now it brings us to deep learning models for solving problems of automatic facial expression and gesture generation. First, the paper Generating Token Face Landmarks from Speech describes a solution for facial landmarks generation. They tested their approach on Lombard grid corpus using facial landmarks detector with 69 points. They also normalized faces alignment to not depend on the face position and its shape. At each time step, the input to the network is the first and second order temporal differences of the log-mel spectra of the current and the previous n frames. They also use delay because we often move our lips before producing a sound. The model itself is LSTM network, but they also tried a fully connected network which has jumps between frames without temporal dependencies. The second paper, Learning Individual Styles of Conversational Gesture, describes an approach for arm and hand movement generation for various speakers. They have a very fascinating video of generated movements on YouTube. They generate arms and hands skeleton movements and then synchronize video, synthesize video using post-to-video method by Chan et al. Based on generative adversarial network. Their model consists of set of convolutions downsampling a log-mel spectrogram to one-dimensional signal followed by U-net mapping this signal to a temporal stack of pose vectors. They also used adversarial discriminator besides L1 norm to check that poses are coherent and real. It is used because one phrase can be said with different gestures. As a result, the proposed motions looks real. Finally, the paper Synthesizing Obama, Learning Lip Sync from Audio presents a system generating Obama speeches from his voice. The most difficult part of this approach is texturing Obama's mouth to make it realistic. However, there is a step of mouth landmark generation. They use LSTM network as model, MFCCs for audio representation, supervised descent method for landmarks detection, and they represent mouth shape by PCA coefficients. And they also provide a very fascinating video of their results. Before we finish, I'd like to briefly mention the method of spectrogram generation from the raw text. There are a lot of approaches for speech synthesis like WaveNet, but this approach generates spectrogram in one of the steps, which can be useful for landmark generation. So, the model has an encoder-decoder architecture with special attention mechanism. Both encoder and decoder are recurrent networks with some convolutions. As input, the model takes character embeddings. So, it seemed to me that this approach can be combined with ones mentioned before to solve text-to-gesture generation problem. And that brings me to the end of my overview of gestures and facial expression generation. Thank you for your attention and have a nice day.